This is the first lecture from Chapter 13, all about solutions. Solutions are made up of two primary components. One is the solute, and that's the stuff that you're dissolving, like if you were making salt water. And the other is the solvent. The solvent is what you're dissolving the solute into. It's not, as you'll see as we go through chapter 13, it's not always easy to know what the solute is versus what the solvent is. So it's important to understand the actual definition of those two. And that is that a solvent is the component that is present in the largest amount. And the solute or solutes, there can be more than one, are the components that are present in smaller amounts. So here we come to where it can get confusing what the solute and solvent are. You think probably of solutions as dissolving a solid solute in a liquid solvent. That's probably the most common, a solid solute and liquid solvent. However, a solution can have any combination of phases as long as one dissolves or totally assimilates with the other one. You can have a gas solution, and actually, as you'll see as I lecture on too, that all gases are completely compatible, and that's basically because they have no intermolecular interactions at all, so they can't even really tell the other one is there, so they mix perfectly well. You can have a gas bubbled into a liquid solution, so that'd be like carbonated water. You can have two liquids, so alcoholic beverages are alcohol and water, which are make a solution. You can even have a solid-solid solution, so metal alloys. Alloys are solution blends of metals. So brass is it copper and silver? Anyway, there are a lot of metal alloys or metal solutions out there. Oh, here, brass is copper and zinc. The most common type of solution are those that have water as the solvent, and those are called aqueous solution. So you'll see a lot of that in chemistry. It's abbreviated AQ. And aqueous means whatever you're talking about is dissolved in water. Couple more vocabulary terms. You'll see references to the solubility of a material. The solubility number that you're given represents the maximum amount of a solute that's able to dissolve in a solvent at a particular temperature and pressure. You'll learn that solubility does depend on temperature, and in the cases of gases, pressure also. The most important aspect of solubility, whether or not something will dissolve in something else, depends on the intermolecular forces involved. There are several intermolecular forces involved, which you'll see in a couple of slides. One more vocabulary. Saturated solution is a solution that has the maximum amount of solute dissolved. And if you ever have a solution with sediment or some type of precipitate settled on the bottom, that means that that is a saturated solution. Okay, that means that it's reached the maximum that will dissolve. Likewise, an unsaturated solution is one that can take more solute. A supersaturated solution, these are really weird, they're odd. The definition seems to be illogical, but a supersaturated solution is one that has more than the maximum amount of solute dissolved. So how is that possible? You kind of have to trick the solution, which the next slide will explain a little bit better. But a supersaturated solution is very unstable, and any little jostle or irritation to it will cause the excess solute to come crashing out as a precipitate. As I mentioned earlier, Gases are infinitely soluble in each other, and so they're an exception. Everything else has a limit to the solubility. There's a special vocabulary word when you're referring to two or more liquids that are soluble, and that is miscible. That C is silent. Remember that, because that shows up in some other problems, and unless you realize it's referring to two liquids, it might mess up your ability to do the entire problem. So alcoholic beverages are an example of miscible liquids. And then we would say two liquids that do not dissolve in one another are called immiscible. And oil and water would be an example of that. So let's look at one common type of solution, and that is air. A lot of people don't realize that the air you breathe is actually a solution. It's a solution of gases. And that's a perfect example of the type of solution where it's not entirely apparent what the solvent is and what the solutes are. So in this case, you have to look at all of the components. And so let's see, nitrogen, oxygen, argon, CO2, and a variety of other ones. And remember the definition of solvent? It's the component that is present in the largest amount. Well, clearly nitrogen is the largest component of the air we breathe. So nitrogen is considered the solvent in the solution air, and all the other components are solutes. You have multiple solutes. We're still mainly going over vocabulary words. Salvation is an important vocabulary word in this chapter. Salvation basically refers to solvent molecules surrounding solute molecules, and salvation is what happens when a solute dissolves in a solvent. Shoo, too many S words. So if you look at this little species here, you can see there is an ion in the middle, and the water molecules are completely surrounded that ion. Okay, so that represents salvation, and salvation must occur in order for something to dissolve. So let's pick apart the process of dissolving. The first thing that has to happen is the solute particles or molecules have to separate. What is holding these solute particles together? Okay, hopefully you remember that from our last chapter, intermolecular forces, right? So the first step involved in dissolving a solute is to break up these forces. That is going to cost energy, right? So anything that absorbs energy or costs energy is called endothermic. I don't know if you remember from the little bit of thermochemistry you had, but if you have an endothermic process, mathematically it has a positive sign, greater than 0. All right, and now let's look at the next step. Just like the solute needs to separate, so does the solvent particles. Solvent particles also have intermolecular forces that must be loosened to make room for a solute that wants to get in there. So separating the solvent particles, separating any particles, is an endothermic process. So the heat value, enthalpy value for it is a positive sign, greater than 0. Now, you might be asking yourself, okay, if it takes energy to separate the solute and it takes energy to separate the solvent, why does anything dissolve? Well, the bonus, the payback, is when you mix the solute particles together with the solvent. Assuming the two particles are attracted to one another, it will be an exothermic process, okay? And that's only if it dissolves, okay? All right. So what happens, you form new intermolecular forces between solute and solvent, and that is very stabilizing, exothermic, but of course mathematically has a negative sign. So the bottom line is, in order for something to dissolve, there's a lot of words here, but you may want to jot this down. In order for something to dissolve, the intermolecular attraction between the solute and solvent must be greater than, stronger than, the forces that used to exist between the solute molecules themselves and between the solvent molecules themselves. So originally, what did you had? You had interactions between solvent molecules, you had interactions between solute molecules, and when you dissolve something, you have to break these interactions up and form new ones in between solute and solvent. That whole process of dissolving or solvation is a process that you should be able to explain briefly in a small handful of sentences or diagrams. All right, so let's look at an ionic compound, let's say salt, dissolving in water. Why? That's just such a common system. Why does salt dissolve in water? It's all to do with intermolecular forces. There's a rule of thumb that is very helpful, and it's like dissolves like. And what that means is polar substances dissolve in other polar substances, and nonpolar substances prefer other nonpolar substances. And it's because of the intermolecular forces. So, what type of substance is an ionic compound? Ionic compounds are the most polar substances around. Okay, remember what polar means? It means there's some development of charge development, some unequal distribution of electrons in the compound. And ionic compounds have all-out charges, so they have very unequal electron distributions. They're very polar. And so ionic compounds will dissolve only in polar solvents. Water, I hope you realize, is polar. Okay, it's a polar molecule. The oxygen is much more electronegative and has a partial negative charge compared to the hydrogens on water. So what happens then, the water molecules begin to surround the ions, and ultimately what you get is, you would call this a solvated chloride ion and a solvated sodium ion. Note the orientation here. We've talked about this before, but the anions are solvated so that the hydrogens in the water molecules are facing the negatively charged chloride. The cations are also surrounded or solvated by water molecules, but what faces the cations are the partial negative oxygen atoms of water. So be able to draw something like that. So here's kind of a bigger picture of what we just went over. When salvation occurs in water, whoops, I don't know where I'm getting that from. In water, we call it hydration. So we say things are hydrated. Same type of thing. They're surrounded or dissolved in water. The type of intermolecular force is called ion dipole. We didn't really spend much of any time talking about that type of intermolecular force. We talked about London dispersion, dipole-dipole, hydrogen bonding, and ion dipole is the key intermolecular attraction when you're dissolving things in solutions. And ion dipole is stronger than all these three guys we focused on in the last chapter. So obviously the ion comes from the ionic compound and the dipole comes from the water molecules. So ion dipole attractions. All right, so here's a typical multiple choice type question that I might ask you on a quiz or test. And so I would suggest turning off the video and seeing how you would answer these, and then I will go over the answers with you. All right, so is iodine, which is one of our diatomics, more soluble in water or in a compound called hexane? Well, when you're trying to decide solubility, you need to look at the polarity. Remember, like dissolves like. Is iodine polar? I'm hoping at this point you're able to say that it's totally nonpolar, as are all diatomics. This is not a polar bond. The electronegativities of the two iodines are identical. So it's nonpolar. And then look at the solvent. Is it polar or nonpolar? I'm hoping that you remember that when you have hydrocarbons, compounds that only have carbon and hydrogen in them, they are nonpolar. The electronegativity of carbon and hydrogen are very similar to one another, so those are all nonpolar bonds. So iodine would be more soluble in hexane and would not be expected to be soluble in water, which is polar. All right, methanol. Would it be more soluble in water or octane? Methanol is polar. Okay, most everything that has a heteroatom, and that's a nonmetal type atom on the right side of the periodic table. We call those heteroatoms because they tend to have high electronegativity. But most compounds that have those are polar, or at a minimum have polar bonds. That's a polar compound. It's also capable of hydrogen bonding, and so it would be expected to be very soluble in water, which it could also hydrogen bonds. Octane is a hydrocarbon. We would expect that to be nonpolar, and therefore we would not expect methanol to dissolve in octane. Alrighty, just a couple more slides. We're about done with this intro to solutions. One of the things I want you to understand, and it's not that critical in this chapter, but it plays a very, very important role in about the last month of this class, and that is equilibrium. When you are dissolving something, so let's look at an ionic compound called calcium carbonate. Every ionic compound, even if it's termed as relatively insoluble, has at least some limited amount of solubility in water. Calcium carbonate happens to be chalk, and so I think you know that chalk, you think of it as insoluble in water, right? But if you have very accurate machinery, you can detect that a small, very small amount of calcium carbonate does in fact dissolve in water. But like any solubility process, it's not a static process. Dissolving is a dynamic process. What the heck am I talking about? Well, there's a set amount of calcium carbonate that will dissolve. We'll call that X. But the calcium and carbonate ions that have dissolved don't remain the same because dissolving and precipitating back out are constantly going on, okay? So as you dissolve, you break apart the ions, they get solvated in water, and then when there are enough of the solvated ions, they actually start recombining and going back to reform the original undissolved solid. And this process goes back and forth, back and forth, back and forth. We call that a dynamic equilibrium. And what equilibrium is, what the definition is, and this is what's really, this is kind of an introduction to later on in the semester. Equilibrium occurs when the rate of a forward process equals the rate of the reverse process. So when the rate of dissolving or breaking apart the ionic compound equals the rate of reforming the original undissolved solid, then we have reached equilibrium. The units for solubility are usually grams of solute per 100 grams of solvent. We will be presenting graphs of solubility, so this is typically what's on the y-axis. And for most solids that you're trying to dissolve in something, I think you know intuitively that solubility increases as the temperature increases. One thing you may not realize is that there's an exception to that trend, and that's the solubility of gases. The solubility of gases decreases as temperature goes up. So think about having a soda, opening up the top, and then heating the bottle. You can almost see the carbon dioxide fizz and bubble out of there, right? The more you heat it, the more the carbon dioxide is like, I'm out of here, and it bubbles out. So the solubility of gases goes down as temperature goes up. So that's an important little tidbit to remember. Solubility curves, you need to be able to interpret those. And so let me show you on the next page what they look like. So here's a typical solubility curve. Notice the units. The y-axis is grams of whatever the solute is over 100 grams of water. Those units are important. Don't forget that the denominator is 100 grams of solvent. Temperature is the x-axis. And so let's look at a couple of these for a minute. There are a lot of questions that you need to be able to answer if you have a solubility curve to look at. So look at the shape of these lines. In general, the solubility increases as temperature increases. Just as we said, makes total sense, right? If I told you to look for trends and exceptions, if somebody told me to do that, let me put it that way, I would look at this blue line and I would say, you know what? Whatever that blue line is doesn't change much with temperature. I wonder what it is. It is sodium chloride, table salt. So heating up a solution of sodium chloride doesn't help that much, but in general, most everything that is a solid gets more soluble with increasing temperature. Take a look at the solubility of gases, though. As I said, their solubility goes down with increasing temperature. Let me ask you real quick a typical question. What if I asked you, what is the solubility of sodium nitrate? Okay, you need to remember your naming rules, so you might have to brush up on those. What is the solubility of sodium nitrate at 50 degrees Celsius? Well, first of all, you'd have to find sodium nitrate. That's the orange line. And the line represents the saturation point, which is the maximum solubility. Then you'd have to find 50 degrees and walk your way up to the curve. And you'd have to say, okay, the solubility of sodium nitrate at 50 degrees is about maybe 118 grams per 100 grams of water. And so what if I put 150 grams of sodium nitrate in 100 grams of water? What would happen? Well, 118 grams would dissolve. How many grams would remain undissolved in the bottom? 32 grams would remain undissolved in the bottom because that's beyond the saturation point. So make sure you're real familiar with solubility curves. All right, so let me ask a few more. Rank these ionic compounds for their solubility in water at room temperature, which is about 25 degrees. So room temperature is typically thought of as around 25 degrees Celsius. Rank from an increasing order. So turn off the video, make sure you can do it, and then I'll go through it with you. The first thing you need to do is mark 25 degrees, and then you're going to want to mark every single substance at 25 degrees. There. And so the one with the lowest solubility is potassium chlorate, then potassium dichromate, then potassium chloride, and then sodium chloride, potassium nitrate, lead nitrate, and this is a really weird one, sodium sulfate. I'm not really sure why it goes down. Let's see, then sodium sulfate is very soluble, and then calcium chloride is also very soluble, and the most soluble at 25 degrees is sodium nitrate. Interesting. Now, if I asked you to do the same thing to list in increasing order the solubility of these salts at 75 degrees Celsius, would it be the same? Let's look. Well, the lowest solubility is potassium chlorate, which I left off the C. Yeah, so that's the same. The next one is sodium chloride. So notice that the order that I'm going to put them in are different, okay? And the solubility of these are so high at 75 degrees, they're off this chart. But I guess the point I'm trying to make here is the order of solubility will change with temperature, so don't assume it stays the same. One more question. If I add 50 grams of sodium chloride, table salt, to 100 grams of water, what type of solution would I have? Would it be saturated or unsaturated? And explain how you know. So, let's say room temperature, so 25 degrees Celsius. All right. So 25 degrees Celsius, let's find sodium chloride. It's right here. And it looks like about 34 grams of sodium chloride will dissolve in 100 grams of water. But I said I added 50 grams. So that means I will have a saturated solution of sodium chloride with 50 grams minus 34 with 16 grams of sodium chloride undissolved, probably sitting at the bottom of the container. So that's it for the first lecture in chapter 13.